Alrighty, hello and good afternoon for our final lecture of the semester. I can't believe we're already here. I don't know if it's taken way too long to get here, or if the semester's blown by. Probably some combination of both. But we're here at the end. So hello, welcome, good afternoon, and if you're tuning in at another time, good evening or good night, possibly even good morning, depending upon how much after the stream you're watching this. All right, so today we are going to conclude. We're talking about the last thing we're going to talk about in Chapter 11, and then hit on one topic in Chapter 12, specifically boiling point elevation and freezing point depression. And those are the topics that are covered on Lab Exercise 8. So this is that material that you'll need to do that worksheet. All right, so let's go ahead and dive in. So the last topic that we're going to cover in Chapter 11 is a subject called called phase diagrams, but I need to adjust both my eraser and anytime I work in Photoshop in between streams, the brush sizes get all messed up, and by get all messed up, I mean I change the brush sizes depending upon the project, but it's always a surprise. Okay, we're where it needs to be. So phase diagrams. All right, our final Chapter 11 topic. So a phase diagram is a plot of how the phase of a substance changes as temperature and pressure change. So a phase diagram has a y-axis and an x-axis, and pressure is on the x-axis and temperature is on the y. All right, and it's a map of how what phase a substance will have at any given pressure and temperature, and they all somewhat look like this. So there's usually some point around here, and then two lines split off, kind of going like this, one going like so. And actually, I hate to be perfectionistic like this, I'm actually going to redraw this. I want it to be a little shallower, just given the space we have to work with here. All right, so the phase diagrams will have these three basic regions to them, and these are in each region. This is what each region represents. This is where the substance is a solid. Down here is where the substance is a gas, and then in here, the substance is a liquid. And so, kind of, if we're going to add some color, over here we're dealing with liquids. Down here we're dealing with gases. And then in here we're dealing with solids. All right, and Actually, I'm just gonna color this in just a little bit more. Okay. And let's just I just want to make this line a little more bold. That point's important. This point is important. And we'll talk all about it. Okay, so this is all phase diagrams more or less look the same, and the regions, solid, liquid, and gas, all fall in the same general regions in each phase diagram. Emma, happy Wednesday. Happy Wednesday indeed. Now, so just to cover, so just so you know how to read a phase diagram. Let's say you have a substance at a given pressure and temperature. All right, and so if you marked, so if you have a substance that's at a certain pressure P1 and a certain temperature T1, all right, and I'm going to use green to kind of highlight. Let's say that your substance's pressure, let's say P1 is right here, and T1 is right here, to determine whether or not that substance was a pressure, to determine whether or not that substance was a solid, liquid, or gas at that pressure and temperature, all you have to do is see where that pressure and temperature intersect on your phase diagram. And as you can see, the intersection of P1 and T1 on this diagram is in the solid region. So the phase that this substance would have at this pressure and temperature, the phase would be a solid. All right. Let's say that the pressure and temperature were different. Let's say that the pressure was down here and the temperature was over here. Well, again, to find the phase of your substance, you look at where P1 and T1 intersect, and here that intersection is in the gas region. So we would say at this pressure and temperature, the substance would be in the gas phase, all right? And I'm sure you can imagine a pressure and temperature that would fall in the blue region. That would be in the, that would mean that that substance is a liquid at that pressure or temperature, all right? Now, let's talk about these bold lines, all right? These lines right here, oops, nope. Let's open up a new thing. So let's talk about the border regions, the borders in between the solids, liquids, and gases, all right? These regions right in here all represent phase transitions. All right, so these are phase transitions. Oops, running out of room. All right, those borders of the regions between solid, liquid, and gas represent the pressures and the temperatures at which the transitions occur. All right, between phases. So a little bit of a refresher. So if you look at this border, let's see. I need a different color. And something that'll contrast a little better. So if you look at this border right here, this represents two transitions. It's the two transitions between the liquid state and the solid state. So this will represent, not boiling, this will represent freezing which is, oops, this represents freezing, which is the transition of a liquid going to a solid. Oops, sorry, not a parentheses, a solid. All right, and it represents the transition of melting, which is a transition where a solid becomes a liquid. All right, that border, that exact border represents the transitions freezing and melting. All right, this transition, this border right here, between solids and gases, this represents the transitions of sublimation all right, and sublimation is the transition where a solid goes straight to the gas phase, skips the liquid phase, goes straight to the gas phase, and this represents the transition of deposition, where a substance goes from the gas phase straight to the solid phase. All right, so both sublimation and deposition are represented by that border. Finally, the third transition, right here, the border between the liquid and gas phase represents boiling and condensation. Condensation is when you go from a gas to a liquid, and boiling is when you go from a liquid to a gas. All right, so those are the 6 transitions between states, and the transition. Each transition is determined by the 2 phases that it separates as a border, right? So liquid and gas, you got boiling and condensing, solid liquid, melting and freezing, solid gas, sublimation, and deposition. All right. Now, you can use the phase diagram to determine. You can determine any transition point. You can determine the temperature at which a substance will melt or freeze or boil or sublime under any given pressure. So you can determine transitions. Or I should say, you can determine transition points. systems. You can determine transition points using using your phase diagram. All right, and here's how. Let's say you want to know what is the melting point. Oops. Let's say you want to know what the melting point of a substance is at P1 at a given pressure. Well, what you do is you have to find where P1 is on the graph, and then you look to see where does P1 intersect that transition border. For melting, it's the border between solids and liquids. So at P1, that particular substance would melt at T1. So this would have a melting point of T1. All right. Let's say you change the melting point. Let's say we want to know what the melting point is at a different pressure. We'll call it P2. Well, you find P2 wherever that falls on your phase diagram. You look to see where P2 intersects with the melting transition, and then trace that down and find your temperature. The melting point at this second pressure is this temperature that I've labeled T2. So the properties, the points of the transition, melting point, freezing point, boiling point, sublimation point, they change. Those temperatures change as pressure changes, and you use the curves in your phase diagram to determine what those are. So that's kind of how you use a phase diagram. This is also, you may not realize that something like boiling points, melting points aren't constant things, that they are changing. They do change. And that's why, for example, as you can see here, for example, you can see that T2 is larger than T1, right? T2 is greater than T1, and you also see that it's because P2 is greater than P1. So at a higher pressure, there's a higher melting point. At a lower pressure, there's a lower melting point. This is also true for boiling points, for example. So if you are on vacation, you're camping, you're up at Tahoe, you're at a higher elevation, which is a lower atmospheric pressure. Because you're at a lower atmospheric pressure, that means that the boiling point of water is lower. So you maybe have a pot on the fire and the water's boiling, but that temperature is lower. So for example, it'll take a little bit longer to cook your food, to cook your noodles, because it's not boiling at 100 degrees Celsius, it's boiling at a lower temperature because you're at a lower pressure. All right, these things are relative to the conditions under which we're doing whatever we're doing, whether it's boiling water, melting things, all that stuff. So anyways, and phase diagrams show us exactly how those things change relative to each other. All right, let's talk about there's two critical features of a phase diagram that we need to dig into. The first is what's known as the triple point, which is right here. Now, each phase transition whether we're talking about melting, boiling, subliming, all those transitions. Actually, I should, before we get there, these transitions, each one of them, right here, the transition curve, or actually, I need to start this a different way. At each transition point, and this is true whether it's melting point, boiling point, freezing point, sublimation point, at each transition point, two phases of matter coexist simultaneously. All right, what this means is at the melting point, for example, both solid and liquid exist together. All right, this is something that's that might be surprising, because you might think melting means you're going from ice to water, right? And that is the transition. Melting, you are going from ice to water. You're going from a solid to a liquid. But at the melting point, at 0 degrees Celsius, under 1 atmosphere of pressure, you actually have both solid and liquid molecules coexisting simultaneously. So at 1 atmosphere, the warmest ice can get is 0 degrees Celsius, but the coldest water can get is 0 degrees. They both coexist at that temperature. That's why, for example, if you have a cooler outside and you're like barbecuing, and you've got a bunch of drinks in the cooler, the drinks will actually be colder if you have a mixture of ice and water in there. If you have a healthy mixture of ice and water, the ice and water will both be at 0 degrees Celsius, and ice are chunks, but water will totally surround each object, so the bottles will be totally covered with 0 degrees Celsius if there's some water mixed in there with the ice, as opposed to if there's just solid ice in your cooler. You're not going to get total surface area coverage of your beverages, and they are not going to get as cold as they would if they were totally covered by water at 0 degrees Celsius. So at each transition point, both phases exist together. Now, there is one very special place on the phase diagram where all three meet, and this is called the triple point. Right here, I'm going to call this, and you can find the temperature and the pressure of the triple point. And if at each transition point 2 phases can coexist simultaneously, at the triple point, all 3 phases of matter exist simultaneously. All right, all 3 phases of matter. So at the triple point, you can have a solid, a liquid, and a gas all coexisting together at that temperature and pressure, and you find the triple point where the 3 meet in the center. So that's one thing you should be aware of, be able to pick out. The other point that that you should know of is right here, and this is called the critical point. You may have originally thought that I just got lazy and didn't finish drawing the barrier between liquids and gases, but I actually stopped on purpose because that barrier between the liquid and the gas does not actually extend forever. The critical point is after the critical point, which is so I should say after the critical point. And these are usually very extreme pressure and temperature conditions. The gas and liquid, I should say that gases and liquids. Gases and liquids. Running out of room. Let's do this better. There we go. Gases and liquids cease to be two distinct phases. All right. Anything that exists kind of out in this region, this is where you find things called supercritical fluids. And they're a little bit like gases, they're a little bit like liquids, and depending upon what the pressure or temperature is, they could be more like a liquid, more like a gas. The higher the pressure is, the more dense they'll be, they'll behave more liquidy. The lower the pressure is, the more gaseous they'll be, but there's no longer any clear separation between liquids and gases. And specifically, it really in this region is where you find the supercritical fluids tend to be mostly in here. Right in there. Examples of supercritical fluids. This is actually how all of our dry cleaning happens. They actually take carbon dioxide, which is a gas, and pressurize it till it gets into that supercritical fluid region, so it's not a pure gas anymore. It's kind of like a liquid, kind of like a gas, and they press that through all our clothes, and that's what removes all the nasty stains. It's supercritical CO2. So it's, again, usually very extreme conditions, but that end of the liquid gas barrier is called the critical point, because after that it becomes ambiguous where the gas phase ends and the liquid phase begins. All right, and that is the end of chapter 11, and now we are going to talk about the last thing we're going to discuss this semester, which is the topic of we're going to be talking about colligative. Whoa, hold up. Colligative properties. All right, colligative properties. So, and again, so a colligative property is a property of a solution that changes depending upon the number of particles present. All right, it's any property It's any property of a solution that changes with the number of particles present in the solution. All right, that is the definition of colligative properties. There's many colligative properties out there, but our focus here is going to be on boiling point and freezing point. So that's going to be the emphasis that we're going to make on those two colligative properties specifically. There we go. Boiling point and freezing point. All right, and something to be aware of. What we're about to discuss right now is I'm about to lecture on the material on exercise 8. All right, the exercise 8 material. So if you hopefully you haven't started it yet. I mean, if you have, that's fine. But we're going to talk about what you need to know to complete those exercises. That exercise, sorry, there's not more than one. Oops. All right, so let's take a look here. So boiling point and freezing point. Now, so the boiling point and freezing point of a solvent changes when you add solute to that solvent. All right, so the presence of solute will change the temperature at which it boils and the temperature at which it freezes. And I'm going to tell you up front how those changes occur. All right, so when you add a solute to a solvent, there's two things that happen. So adding solutes to solvents causes, the first thing it causes is, well, these happen simultaneously, but we're listing them. Boiling point elevation. So the boiling point of the solution rises, it's greater than the boiling point of the solvent. And the second thing it causes is freezing point depression. So adding solutes to a solvent simultaneously raises the boiling point, so the boiling point of the solution is greater than that of the solid, and it decreases the freezing point. The freezing point of the solution will be lower than the freezing point of the solid. And if you're wondering, of the solvent. And if you're wondering why, the answer to that question lies that explanation involves intermolecular forces. So to understand this, you have to consider what intermolecular forces are active and present in a solution versus in a solvent. All right? So this is our pure solvent versus our solution. And so to represent our solution, I'm just going to add little green solute particles. All right. When we're talking about a pure solvent, the only things present here are other solvent molecules. So the only intermolecular forces around when you have a sample of pure solvent are the intermolecular attractions between individual solvent molecules. So there's solvent molecules being attracted to other solvent molecules, and that is the only intermolecular forces present. This is not the case when you have a solute dissolved in a solvent. You do still have the solvent-solvent attraction, right? Solvent molecules attracted to other solvent molecules. But in addition, you also have the attraction between solvent molecules and the solute molecules. All right? So you have still the solvent-solvent attraction. But now, once you dissolve the solute, there's also the solvent-solute intermolecular attraction. In other words, there are more attractive forces present in a solution than there are in a pure solvent. Right, and that is the conclusion. So there are more attractive forces present in a solution than a pure solvent. Emma, can a solute and solute? Yes. Okay, Emma, great question. Great question. So, Emma just asked, can a solute and can solute molecules have attraction? And the answer is yes, absolutely they can. However, there's something when you dissolve a solute in a solvent, there's something that happens, a phenomenon called they form a solvent cage. So, yes, the solute molecules are attracted to other solute molecules, but what happens when you dissolve them in a solvent is all the solvent molecules kind of surround the solute and pull them into solution. So even though the solute molecules do have an attraction to the other ones, they never get close enough to another dissolved solute molecule for that interaction to build up, because the solvent molecules are so eager to get around and surround and get those attractive forces going that the solute molecules never get an opportunity to get close enough to another solute molecule to have that interaction. It's kind of a way to think about it, and this is an imperfect example, but think about when a famous person is showing up to a red carpet event. They're just surrounded by paparazzis, right? Snapping pictures, all these cameras, all the press, so eager to see that celebrity, and the celebrity is like the desired solute molecule. The solute molecules, celebrities at these things will bump into each other from time to time and do something famous, and we all gawk, and we're like, oh my gosh, I can't believe that person just met that person. But they never hang out that long because they're being surrounded and dissolved by all of the press and all of the adoring fans and all that stuff. So it's possible, but when they're in solution, it's like a celebrity on the red carpet. They're just almost all the time surrounded by solvents, right? By the paparazzi and press, not other famous molecules. So because it's so infrequent, we don't really consider the solute attraction in a solution solution because it is almost entirely, in like over 99%, solvent attractions and solvent solute attractions. The reason why we still consider solvent attractions is the solvents all are still bumping into each other trying to get close to the solutes. Yep, exactly, Emma. That is exactly it. So, again, now pulling back kind of big picture, there are more attractive forces present in a solution than in a pure solvent. And so when you think about the process of boiling, for example, all right, when you think about taking a pure solvent through the phase transition of boiling, this process will destroy all the solvent-solvent interactions, because you're going from a liquid where the matter is relatively dense, it's bumping up against each other, to a gas where they're all separated out. So when you boil, the process of boiling destroys all of those attractive interactions, which for a solvent means, a pure solvent, you lose all of the solvent-solvent interactions, all right, but for a solution, when you boil a solution, you turn the liquid into a gas, right? So the liquid flies away, but the solute remains behind, right? There's that crusty solid leftover. And so here, when you boil off the solvent of a solution, you're losing the solvent-solvent interactions, and you're losing the solvent-solute interactions. All right? You're losing the solvent-solvent and the solvent-solute, because we're breaking up more intermolecular forces intermolecular interactions. This requires more energy. And that is why the boiling point of a solution is higher than the boiling point of a solvent, because we have to put more energy in to break up all the intermolecular attractions, right? The way to think about it is the attractions are holding the molecules together. To take this thing into the gas phase, we have to pull them apart, and the more interactions that there are, the more yanking we're going to have to do, the more energy we're going to have to invest to separate all these molecules from each other. So adding a solute will elevate the boiling point. All right, now the freezing point drops. It's we said it was boiling point elevation and freezing point depression. Now the reason why the freezing point is lower is similar to the it's similar to the reason for why the boiling point is elevated. It's slightly different though. So when you look at a solution, right, it's in the liquid phase, all the solute molecules are free to kind of slosh around, and you get tons of solute-solvent interactions, right? Like we said, the solvent molecules are surrounding every single solute molecule because they want to get as close as they can to all these famous little green dots, and it maximizes all the solute-solvent interactions. All right, the solvent molecules are cramming in as much as they possibly can. When you freeze, a solution, what happens is it doesn't free with each solute surrounded by a solvent molecule. The solute tends to clump together. So once you freeze, chunk, we got solid ice or whatever we have, but then we tend to have these lumps of solid material, actually, they kind of clump together and freeze out of solution. And the thing is, when you freeze them, it's not, you don't lose all of your solvent-solute interactions, because there's this border region between the clumps of solid solute and the clumps of solid solvent. There's this border region where you still get some interactions, all right? So when you freeze, we don't lose all solvent solute interactions. But we lose most of them. All right, we lose most of them because now we no longer have a scenario where each individual solute molecule is surrounded by solvent. They're kind of clumped together. We've lost a lot of those solvent-solute interactions. As a result, we have to drain a lot more energy out of our solution to get our solution to freeze solid, more than we would have if it were just solvent molecules, because if it's just pure solvent, they're all sloshing around, you try to freeze them, they're like, cool, chunk, just solvent molecules, but they're not losing the solute-solvent interactions. So as a result, we have to pull more energy out of a solution to get it to freeze, and that will lower the freezing point. All right, so let's talk about looking at and actually calculating how the boiling point and freezing points of solutions will change as we add solute. So there's an equation for boiling point elevation, and that is the change, whoops, need to open a new slide, the change in boiling point is equal to I times something that I will call molal times KB. All right, let's talk about what each of these are. So this right here is the change in the boiling points. All right. I is something called the Vant Hoff factor. Now molal we'll talk about this is molality. It is a new concentration unit. It equals the moles of solute over the kilograms, not of the solution, but of the pure solvent. All right? Something to know about molality. It's technically, the symbol is an italics M. All right. The symbol for molality is an italicized M, which is very easy to confuse with mass. Mass is the symbol for mass is an unitalicized M. Molality is italicized M. So when you notice kind of a slanty M, that is molality. Now, in lecture, I'm just going to write molal out for that, mostly because, as you can see here, my ability to write in italics is almost non-existent. And so I don't want you to think that I'm writing in mass when actually I'm dealing with molality. But in your textbook, it'll write this as an italicized M. It's very subtle, it's very easy to miss, so don't think that it's mass. It's actually molality, which is moles of solute over kilograms of solvent. And finally, Kb is the boiling point elevation constant. And the only thing to know here is that it is a unique to each solvent. So each different solvent has its own unique Kb. So you just have to look those up. All right. Let's talk about what the Vant Hoff factor is. That's the one thing we haven't covered yet. The Vant Hoff factor. Oops. All right. The Vant Hoff factor is the number of particles a solute forms in solution. All right, the number of particles a solute forms in solution. What's that? Well, for example, aqueous sodium chloride, we know, this is an electrolyte, splits into sodium cations and chloride anions. So this would have a Vant Hoff factor of 2, because one molecule of sodium chloride generates 2 particles in solution. Magnesium chloride splits into magnesium cation and chloride anion. This has a Vant Hoff factor of 3. All right. A molecule of sugar. This is a covalent compound, right? It does not ionize into anything. So this would have a Vant Hoff factor of 1. All right, so that's just what the Vant Hoff factor is. You look at your solute, you ask, how many particles does this break into? Oh, sorry, my sloppy is my sloppy's a little writing. My writing's a little sloppy. Sorry, Emma. It's Vant with a with an N. Something to know, because you might run into this from time to time. For strong acids, like, Emma, you are so totally welcome. Like, for example, HCl. Acids are covalent compounds, but they can ionize. And strong acids, we assume ionize completely. So, for example, hydrochloric acid would have a Vant Hoff factor of 2. But weak acids, it's not that they don't ionize at all. They do ionize a little, but they remain mostly associated. So, for example, a weak acid like acetic acid predominantly remains associated, and so weak acids this semester, we just assume that they have a Vant Hoff factor of 1 if you run into that while working problems, etc. If you see a weak acid, just give it a Vant Hoff factor of 1. You'll spend more time in 401 looking at chemical equilibria, acid-base equilibria, and understand why this is a good assumption. So take next semester if you want the explanation, but for now you can just use Vant Hoff factor of 1 for weak acids. All right. Now, I gave you the equation for boiling point elevation. Boiling point elevation has this equation, just rewriting it. The change in boiling point is equal to the Vant Hoff factor times the molality of the solution times the boiling point elevation constant. The freezing point depression is pretty much the same. The change in the freezing point is equal to the Vant Hoff factor times the molality of the solution times, this is the only difference, it's a different constant. It's the freezing point depression constant. So you just have to look up a different constant, but the equations function the exact same way. One thing that I do want to mention, actually, is the boiling point elevation constant and freezing point depression constant have the same units. All right, their units are in degrees Celsius over moles per kilogram. All right, you'll notice that it's the units of molality in the denominator because you need to cancel. Right, you got units of molality here to cancel with the units of molality here and leave you with degrees Celsius, which is what we're calculating. After all, we're trying to find the change in boiling point or freezing point. All right. The last thing that I want to mention before we dive in, we're going to do some examples and then call it a day for the last time. Is you're going to run into problems. So just be aware. Be aware of this. You're going to run into problems that say what is the boiling point or your freezing point? They could also ask you for freezing point of a solution, and then they'll give you more information, all that you need to solve it. The thing that is critical to remember is that it's boiling point elevation and it's freezing point depression. When you find your delta TB or delta TF, those are the changes in boiling point or freezing point. So the boiling point for a solution is equal to the boiling point of the solvent, the pure solvent, plus the change in boiling point. What you're calculating with those calculations, it's not the new boiling point you're finding, you're just finding how much it changes. So you have to add that change in boiling point to the boiling point of the pure solvent. Likewise, when you calculate the freezing point of a solution, remember it's freezing point depression, so you take the freezing point of the pure solvent, all right? Freezing point of the pure solvent, and you must subtract the change in the freezing point, because that change in freezing point tells you how much the freezing point drops, all right? So that's one subtle thing that I see a lot of mistakes made. They'll say, what's the boiling point of a solution? And a student will find the change in boiling point, but that's not the boiling point of the solution, that's just how much it changes from the initial boiling point, the boiling point of the solvent. So you have to remember, add your change in boiling point to your pure solvent, subtract your change in freezing point from your original solvent's freezing point. All right. With that in mind, let's tackle some examples. All right. So let's start with this one. Let's determine the boiling point of an aqueous solution determine the boiling point of an aqueous solution. Oh wait, hang on. We will do this problem. I don't want to start with this problem though. We'll do it. Just give me a second. So let's start with this one. What is the freezing point of a solution with 21.5 grams of copper 2 chloride dissolved in 4.50 times 10 to the second grams of water. When you do these problems in the book, they will not give you what the freezing point of your solvent is, or what the freezing point depression constant is. So you have to look those up. The freezing point of water is 0.00 degrees Celsius, and the freezing point depression constant is for water is 1.86 degrees Celsius over units for molality, moles per kilogram. All right, so always step number one. What are we trying to find? We're trying to find the freezing point for a solution. So right out of the gate, we're going to write that equation. The freezing point of a solution is equal to the freezing point for the solvent minus the freezing point depression, right? The change in freezing point. Now let's look at what we're given. The first thing we're given is actually not in this problem, but it's vital to solving it, and that is the change in freezing point has an equation, right? It's equal to the Vant Hoff factor times the molality of the solution times Kf. Molality also has an equation, so we're going to write that out. The molality of a solution is equal to the moles of solute over the kilograms of solution. No, not of solution, sorry, of solvent. It's critical to keep those distinct, because if I did kilograms of solution, I would get the wrong answer. All right, so that's the equation for molality. We've written down a lot of things that were given. We haven't even started looking at the problem, so let's take a look. We have 21.5 grams of copper 2 chloride, and this is the solute. All right, that's here. We're also given the mass of solvent, 4.50 times 10 to the second grams of water. All right, this is our solvent. You'll notice solvent's right here, but we got to do a unit conversion. 2 unit conversions actually, because our solvent is given to us in grams. Our solute is given to us in grams. We need kilograms of solvent and moles of solute, so we've got a couple unit conversions. But once we do those, we'll have enough information to solve for molality. We've been given our Kf. We've also been given our freezing points, right? So we got this guy. The question is, really the last question is, what about this Vant Hoff factor? That comes from the solute. If you look at copper chloride, this will break into 1 copper cation plus 2 chloride anions. So the Vant Hoff factor here will be 3. So we have to do a couple unit conversions, and then we're off to the races for calculating our change in freezing point. So let's start with our unit conversion for our mass of water, our solvent. That's grams of water. We need to convert to kilograms. So we put grams in the denominator, kilograms in the numerator. Grams cancel. And this equals 0.450 kilograms of H2O. So that's our mass of water of solvent in kilograms. Next, we need to convert our mass of copper, copper 2 chloride, to moles. All right, so we need to put grams of copper 2 chloride in our denominator, moles in our numerator. And I need to grab my periodic table. So let's see. So we got to calculate. Copper has an atomic mass of 63.55 AMU. Chlorine has a atomic mass of 35.45 AMU, but we have 2 of them in the mix. Let's see, now I need my calculator. So 35.45 times 2 plus 63.55 gives us a molecular mass of 134.45. Wait, is that right? 63.55. Yeah. Okay. So that's 134.45. Oops. 134.45 grams of copper cancel. And we've got 21.5 divided by 134.45. And that comes out to be 0.1599175 moles of copper 2 chloride. When you look at our sig figs, we're limited by our initial mass only has 3, so we can only keep 3. I'm going to wait to round to the very end of the problem. We are now ready to calculate our change in freezing point. Again, it's equal to our Vant Hoff factor times our molality times our freezing point depression constant. So our Vant Hoff factor here is 3. Our molality is moles. Over kilograms. Oops. Our kilograms are 0.0450 kilograms, and then 1.86 degrees Celsius over moles per kilogram. When you look at your units, kilograms cancel, moles cancel as well. And so now let's crunch our numbers. So we have 3 times 0.1599175 divided by 0.450 times 1.86. So our change in freezing point is 1.9828933 degrees Celsius. Again, we're limited to 3 sig figs. Actually, everything in this calculation had 3 sig figs. Now, it's important to remember that this is just our change in freezing point, that the freezing point of the solution is equal to the freezing point of our solvent minus our change in freezing point. We're dealing with water, though, which happens to have a freezing point of 0.00 degrees Celsius minus 1.9828933 degrees Celsius. Now, because water's freezing point is 0, our change in the freezing point of the solution will actually be equal to our change in freezing point. But don't get lulled into a false sense of security, because that only happens for water, because water freezes at 0. Everything else freezes somewhere else. And so I don't want you falling into that trap, which is why I took the time to write this extra step out. But we say then that the freezing point for our solution is, the solution will freeze at negative 1.98 degrees Celsius. That's 3 sig figs. All right, so that is that problem. Not too shabby. I have 3 more examples made But let's take we don't have time for another 3. We probably are going to go over, but let's take the hardest one that I have brewed up here. This will be a good one to end on. A nice, challenging example. So, determine the molecular weights of a weak acid if a solution contains 45.0 grams of acid per kilogram of solvent. And the solution freezes at negative 0.88 degrees Celsius. The freezing point of the solvent, or I'm going to say, actually, sorry. The solvent is water, which means that it has a freezing point of 0.00 degrees Celsius and freezing point constant of 1.86 degrees Celsius over molality, moles per kilogram. All right. So, this is a challenge, right? First and foremost, what we're trying to find here is a molecular weight. That might seem totally out of left field, all right? But let's think about what a molecular weight is. It is the grams per mole. And if you think about it, we know the number of grams right here. We were told that there are 45 grams of acid per kilogram of solvent. So we've got our numerator. We just need to figure out how many moles we have. Let's look at what we're given. So we're given that we have 45.0 grams of solute in 1 kilogram. All right. We're given the change in freezing point. It's negative 0.88 degrees Celsius. Change in freezing point comes with an equation. So whenever you're given a value that is accompanied by an equation, you should write that equation out. The change in freezing point is the Vant Hoff factor times the molality times the Kf. You'll notice that we know what our Vant Hoff factor is because we're dealing with a weak acid. Weak acids have Vant Hoff factors of 1. We also know what our KF is because it was given. All right? And we know our TF. So this equation allows us to solve for molality. What does molality give us? Well, molality is equal to moles of solute over kilograms of solvent. Now check this out. We actually have this is quite cool. We actually know this denominator because it's right here. We're dealing with 1 kilogram. So if we solve for molality, we can determine our moles of solute and if we know our moles of solute, then we have our denominator. All right, so we actually have everything we need to solve this problem. We just have to do some algebra to figure it out. So let's move to that phase. First, we have our change in freezing point is equal to our Vant Hoff factor times our molality times our freezing point depression constant. Step number 1, let's solve for molality by dividing both sides by our Vant Hoff factor and our freezing point depression constant, so we can isolate molality on one side of this equation. So molality is equal to our change in freezing point, our freezing point depression, over our Vant Hoff factor times Kf. All right. Our change in freezing point is negative 0.88 degrees Celsius. Our Vant Hoff factor is 1 because we're dealing with a weak acid, and our Kf is 1.86 degrees Celsius over units for molality. You'll notice that temperature cancels, and that's good because what are we solving for here? We are actually solving for our molality. So negative 0.88 divided by, this is a great place to end, actually. I'm not closing it off now. We're going to finish this problem. But I made a mistake. I made the mistake that I warned you about. Remember how I said that the freezing points for the solution is equal to the freezing point for the solvent minus the change in freezing point? I forgot to use that, and it left me with a sign that messed me up, this negative sign. You can't have a negative concentration. So the second I went to punch this in, I was like, wait, something went wrong. And here's what I forgot to do. I wasn't given the delta TF. I was given the freezing point of solution. This is what I was given. This is the negative 0.88 degrees Celsius. And that equals the freezing point of solution, which is 0.00 degrees Celsius, minus the change in freezing point. This is equal to negative 0.88 degrees Celsius is equal to minus 1 times the change in my freezing point, because that's what 0 minus anything is. And now I need to multiply both sides of this equation by -1, and I find that my change in freezing point is actually a positive 0.88. All right, so I just warned you. I was like, careful, this is an easy mistake to make. And I even said an easy mistake to make for students. Apparently, it's an easy mistake that I made it myself, so watch for it. You should never get a negative concentration. That is a dead giveaway that something messed up, that you messed something up somewhere. So this value here is positive, not negative. Now let's crunch our numbers. 0.88 divided by 1.86. So my molality is equal to 0.473118, and our units are moles of solute over kilograms of solution. I can only keep 2 sig figs because of my numerator here. I'm going to wait to round till the end. Now, why this is important is because we have molality is equal to moles of solute over kilograms of solvent I gotta multiply both sides by kilograms of solvent. To find my moles of solute. Oops. So that equals kilograms of solvent, which there's 1 times the molality that I just calculated, 0.473118, and that's moles per kilogram. Kilograms cancel. So I have, and again, there's 3 sig figs in this. 0.473118 moles of solute. Now we're ready to calculate our molecular weight, because molecular weight is equal to the grams of our solute divided by the moles of our solute. So our mass of solute was given, it was 45.0, and our moles we just found 73118. And now we just divide one by the other. So the molecular weight of our weak acid is 95.1136364, and our denominator has 3 sig figs. Our numerator has 3, so we can keep 3. Our molecular weight is 95.1 grams per mole. All right, and that is our answer. You're going to encounter problems like these on the worksheet. I think this example is one of the more challenging ones, so it should help you in that respect. Thank you everybody for hanging out. It's been an awesome semester. Was it too? Okay, let me Let me check. Let me just go back. Because I could totally be wrong. Let's see. Oh, you guys are totally right, and I'm totally wrong. There are, whoops. Somewhere I lost count, because there definitely are, whoops, 2 sig figs here. And so this should be 2, this should only be 2, and, whoa, that got messy. There we go. And so this should, there's actually, you guys are totally right, only 2 in my, nope, 2 in my denominator. So there should be only 2 here, so there should only be 2 there. All right, that is my, yep, you guys are all totally right. Thank you for that one last catch. You have all learned well, correcting me on my on my sig figs. Not necessarily how the semester started, but dudes, thank you all for hanging out. It's been awesome. I wish you best of luck on the final and in all your future endeavors. It's been cool, and yeah, we have office hours tonight, and then finals next week. I will. I'm about 95% done. No, that's not true. I'm like 85% done with the final, but I will be wrapping that up within the next day and posting about that soon. So you'll have some more information coming your way then. But yeah, catch you in office hours, and have a good several hours. Yeah. Lauren, I can I will totally post those extra examples so you can get those reps in. Yeah, we all have definitely earned some relaxation this break. It'll be well deserved by all of us. You are all so welcome.